So we've got the question, we've got all the to-be answereds that go along with this. Right? So what we want to go through and do is slowly work our way through it and process all of those individual questions. So let's go ahead and start this process. We're running a reaction between magnesium hydroxide and hydrochloric acid. So our very first step should be to actually draw out a balanced equation, which means we have to be able to interpret the text into an equation. So magnesium hydroxide, what's our symbol for magnesium? Our symbol for hydroxide? OH. Before we continue further on, we should make sure that our formula is correct. What is the charge on magnesium? +2. Charge on hydroxide? -1. Is our formula correct? No. What do we need? We need 2 hydroxides. Why do we use the parentheses? We're doubling hydroxide, not just hydrogen. If we didn't include the parentheses, it would look like we're just doubling hydrogen. Plus, what are we reacting the magnesium hydroxide with? Formula for hydrochloric acid. HCl AQ, nice. We could go through and specify the phase on that. You're right, I just thought it was kind of funny. How do you know you need the AQ? Says it's acid. For the sake of this question, knowing the phases isn't going to be all that important. Is our formula correct? Hydrogen has a +1, chloride has a -1. Our formula is correct. We're then going to go through to make some products. Theoretically, you should be able to predict what the products are without being given any more information. Right, but we're given a little more information, so let's work with that. We know one of the products is, how do you know that? Good, tells you. So our formula for magnesium, Mg, chloride, Cl. Is our formula balanced?
No.
And you know that because magnesium's a +2, chloride's a -1. We need 2 chlorides. Why do we not use the parentheses?
Because
There's only one species there. The parentheses can help you kind of group something so that you know that you're grouping things. It is technically incorrect to show parentheses around that chloride. Okay. Why? Some old white person said that is the rule. You have to follow the rule. Okay? It is kinda, in response to your muttering in the back, I heard that. That's why I didn't record that. It's actually not true. I did actually record that. Plus, what's that? HOH or H2O. Why would you say HOH? Okay. Why is it less confusing? I agree. That makes me feel really good. Because the way I explained it makes it make more sense. Okay. It has to do with the type of reaction we're doing. What's the type of reaction? Neutralization or, thank you, what were you going to say? Double replacement. Okay. If we do the double replacement, we're swapping our hydrogen for the magnesium and we have HOH. We can see that stand out a little bit cleaner if we just write it as the double replacement as opposed to calling it the neutralization. Which answer is more correct? Neutralization. Okay? Because we are technically mixing an acid with a base. Is that formula correct? HOH. Hydrogen has a +1, hydroxide has -1. Is that formula correct? Yes. Okay. Next step is we have to make sure our equation is balanced, so we should go through and check that. Is it balanced? No. Hopefully what you'll go through and do is count each of the atoms. We could go through and look at magnesium. We could look at chloride. We could look at hydrogen. We could look at oxygen, or we could look at hydrogen and OH. Up to you on how you want to go through and balance that. What you should end up finding. Do we need a walkthrough on balancing?
No.
Thank you. 2, 2, and you should be good. Okay? Enthusiasm, I love it. We now have a balanced reaction. Why did we need the balanced reaction? we're trying to convert one species to another species, we need an equation to show how those things convert. So that's why we need that balanced reaction. Just realize this may not be recording audio. And there's nothing I can do about that, unfortunately. So now that we've got our equation, we can start to organize some of our information in here. What stuff do we know about?
How much each thing is?
We have 50.6 grams of magnesium hydroxide. What else do we know? You have 45.0 grams of hydrochloric acid. The last number included in here I'm not going to actually write down yet. That's 60 grams of magnesium chloride. What is that? Assign a name to that number. Fair enough, it is the dry mass. It is our actual yield. So when we go through to calculate a percent yield, it's actual over theoretical. So we're given the actual. The problem is we don't have the theoretical. Okay, to figure out the theoretical, that's where we have to go through and do all of our limiting reagent calculations. Okay, so what we now have to do is determine if I have just 50.6 grams of magnesium hydroxide, how much magnesium chloride could I produce? Well, how do we go through and do that? Math, fair enough. To convert from one species to another, what unit do I need to be in? I need to be in moles. So the very first thing I'm going to go through to do is convert my magnesium hydroxide into moles. Once I'm in moles of magnesium hydroxide, what can I do? Answer the phone. No. We can then convert our moles into moles of magnesium chloride. Once we have moles of magnesium chloride, then we can convert that into grams of magnesium chloride. Okay. So what we're doing is just kind of cyclizing around this, trying to figure out how to do each of those calculations. So how do we convert 50.6 grams of magnesium hydroxide into moles? What conversion do we do here? What do you mean? Yes, our conversion is coming from our periodic table. We're trying to convert grams into moles. What's the relationship between grams and moles? Our molar mass. So what we can do is pull off the periodic table our molar mass. Okay. How we've been solving for these in class. Hopefully we got space down there. Our answer needs to be grams of magnesium chloride. What are we starting with? There it was, grams of magnesium hydroxide. Okay. Those units do not match, so we can set up a conversion factor. We want to get rid of grams of magnesium hydroxide. We need to get it into moles. Why do we need to get into moles? And then we can use the balanced equation to convert that to a different species. So we'll go moles of magnesium hydroxide. Where do I find the conversion factor between grams and moles? The molar mass off the periodic table. So I'll take the mass of magnesium at 24.31 plus the mass of oxygen at 16 plus the mass of hydrogen at 1. And I will not have the correct answer because I need to multiply the oxygen and the hydrogen by 2 because there's 2 of them in the formula. You're punching in a calculator, so give me that number, please. 58.33. Okay. So we now have the moles of magnesium hydroxide. Is that the answer we want? No. So we need to get rid of the units of magnesium hydroxide and get it to moles of magnesium chloride. How do I do that conversion? That's from our balanced equation. The whole thing we started this with was looking at an equation. So we go up to our equation. What number shows up in front of magnesium chloride? 1. What number shows up in front of magnesium hydroxide? Oh yeah, 1 and 1. Look at that. Nice and simple conversion across. I'm now in moles of magnesium chloride. What do I want as an answer? Grams. How do I convert to grams? I need the molar mass of magnesium chloride this time around. So we go back to the periodic table, 35.45 times 2 plus 24.3, and the number is, what was that, 95? 5.11. Yeah, rounding. Okay, 0.21. We now have a theoretical amount of magnesium chloride that could be produced. Okay, so I'm going to keep that in blue. Anybody give me one person? Go ahead, raise your hand if you want to be the one person to give me the answer. Okay, you are now it. What's the answer? The calculation shown at the bottom. 50.6 divided by 58.33 times 95.21. While he's doing that, we should be able to attempt an approximation. I'm taking 50 divided by 60. I'd actually ballpark that as 50 divided by 50. Kind of lazy. That's about 1 times 95. I'm looking at a number that should be pretty close to 95. If I'm getting a number that's way different from 95, that's a problem. What are you giving me?
92.55.
Everybody see and understand what I went through and did with that? Ballpark seems right. It seems a little high to me, but 82.59. That seems a little bit more reasonable. 92 seemed awfully close. Okay. So we can talk about that calculation later, what you actually entered into the calculator. Questions about how we got that number? That number is now our theoretical yield. That is the maximum I could make with the magnesium hydroxide. I can't make any more than that with magnesium hydroxide. Okay. But the question does not end there, because I now react that with 45 grams of hydrochloric acid, which means I now have to go through and do the exact same kind of calculation, except now I'm starting with hydrochloric acid. Okay, so now I'm going to erase all of that lovely work. And I want to be able to convert now my grams of hydrochloric acid into moles. Once I'm in moles, I can then convert it into moles of the product. From the product, I can then go to the mass. Okay? So we're doing the exact same calculation, we're just using different situations. Our answer, again, needs to be in grams of our magnesium chloride, starting with our 45.0 grams of hydrochloric acid. To be able to convert between our species, we need to be in moles of hydrochloric acid. Where do we find the conversion factor between grams and moles? Grams and moles, periodic table from our molar mass from our periodic table, which in this case I don't need a calculator for. Thank you for trying. 36. You thought I didn't need a calculator. 36.45 grams per mole. I'm now in moles of HCl. I need to convert my substance across, so I'll go moles of HCl to moles of magnesium chloride. Where do I find the numbers that go in that? Now I go back to the balanced equation. What number shows up in front of magnesium chloride? What number shows up in front of HCl? 2. Okay. I'm now in moles of magnesium chloride, and I want grams of magnesium chloride. Where do I find the conversion between grams and moles? From the periodic table. which we thankfully had already calculated, and I've already forgotten that number. Was that the 95 something? 95.21 grams per mole. We can again go through, punch it into the calculator, and we end up with our answer being, anybody got it? 117? Wow. So we have a number larger than 1.
58.
So I'm hearing a 58. Going once? Going twice? 58. I got a second confirmation. 58 point what? 58.7 is good enough for me. Magnesium chloride. Okay? Man, this is a lot of work for one question. We still haven't even answered the question. Well, the question was, what's the percent yield?
Yeah, this isn't a cool question.
We'll address the coolness factor of the question in a little bit.
It's a lot of work.
Okay, so now we can erase all of that work because I need space to write stuff. Okay, so we now look at those two numbers, and what we have to decide on is what is our limiting reagent. So we compare those two values and say which one is the smaller one. That is my limiting reagent. So the limiting reagent in this case is the smaller of those two numbers is the 58.7, which came from the hydrochloric acid. My limiting reagent is HCl. Okay. So my theoretical yield for this reaction ends up being 58.7 grams of magnesium chloride. What was my actual yield? 60.0 grams magnesium chloride. How do we calculate the percent yield? Our percent yield will now be our 58.7 divided by 60.0. Okay, since you guys will probably give me a hard time if I don't do it, let's show the units. And we multiply by 100, and we would now have our percent yield probably up in the 90s somewhere. 98 flat? It was actually 97.8, no other numbers? 3 repeating? Okay. What do we provide as our final answer? It'd be 97.8%. Why? 3 sig figs through our calculations. So we end up with 97.8% yield. And I do see your hand over there, just give me a sec. Percent yield of our magnesium chloride. Yes.
It's not actual or theoretical. That's what I have in my notes.
Oh. Sorry. That was actually going to be one of the questions that we wrote out before. This is what happens when you've got allergy brain. Percent yield, actual over theoretical. And this is actually a common mistake, which is why I actually wanted to talk about it. Theoretical. Which means we actually have our actual being 60.0 grams over our 58.7, which gets us a yield of 102.2, which would end up coming in as 102% yield. Okay. Almost guaranteed what other answer is going to show up as a possible answer choice.
97%.
That 97.8%. Okay, both of those are going to show up as a possible answer choice. The one you would need to provide is the 102% because that's how you calculate a percent yield. It's always actual over theoretical. So thank you for pointing that out. Why does that look weird right now?
It's hard to have more than 100% of something.
How can we ever have more than 100% of what we theoretically should have gotten?
You did something wrong.
You did something wrong. Does that mean your calculation is invalid? Maybe. That is possible. We would really hope that you didn't go through all of that work to find out you made a calculation mistake and you have to repeat the question again. Theoretically, that is what you would do. You would repeat the calculation and you would do it all over again. In the lab environment, you would repeat the calculation again. You get the same result. What does that mean? You still did something wrong, but it's not with your calculations or your understanding of how to do those calculations. It's because you did something wrong in lab. Either you mismeasured something to begin with, okay, or maybe you made a mistake somewhere else measuring something out. Okay. One of the last possible options, when you go through and obtain a product, you're almost always isolating that product away from a liquid. We take a solid and we separate it from the liquid. How do you do that? How do you separate a liquid from a solid? I would argue you don't just dry it out. There's an easier way to do that. Letting it settle, that works too, sort of. So if I took my little beaker here, that's a beaker, there's my liquid, and there's my solid. Sure, my solid is now at the bottom of the beaker and the liquid's on the top. But that's not separated. I now have them separated within the same container. That doesn't quite count. I need to remove the water, or remove that liquid. How can I remove the liquid?
Evaporation.
There's an easier process. How many of you drink coffee? Really? Only like 2 of you? Okay. How do we deal with coffee? You take a filter, you put all the coffee beans in the filter, and you pour the hot water over the top. The hot water goes through, and all the solid junk stays on top of the filter. You've now separated the solid away from the liquid. All we've got to do here is filter. And now most of the liquid is separated out, and we'd have the solid. Okay? Those of you that have had coffee and had to deal with these filters, how dry is your coffee after you've poured the water through? It's not. It's usually soaked in solvent or soaked in water. How can we now get rid of that small amount of water? Now you can evaporate. Okay? There's no point evaporating from the get-go because you're now going to remove way too much. That's a lot of energy you have to put into that. Think minimal energy. I know you guys are already thinking minimal energy, right? You don't want to put in more work than you have to. Filter first, then heat. Okay? That allows us to then separate those away from each other. Your crystals are now wet, though, after that filtration. What if you went and weighed them right then? They'd be heavier than they theoretically would be. There's still water on it, and you're now saying by that measurement that it's all your product, it's all that solid. So is it possible to get over 100% yield? Yeah. You've gone through and made some kind of mistake within your logic or within your experiment to get that greater than 100% yield. Should you ever report something higher than 100% yield? Probably not, because what you're admitting by getting 100% yield or more is that you screwed up. Okay? By then reporting that, you're now announcing to the world that, hey, I screwed up. Okay? So it's usually not a good idea to report greater than 100% yield. Yes?
So basically, we took the 50.6 grams of the magnesium hydroxide and 45 grams of hydrochloric acid.
Yes.
And then we converted them both to the magnesium chloride because that's what we're trying to get the answer to.
Yes and no. Are you still going with that, or are you done with that?
Just like, explain to me what the difference is.
Okay, so what we did was we took magnesium chloride, or what is it, magnesium hydroxide, hydrochloric acid, 2 amounts. We mixed them with each other. Okay. Those two will react in some fashion, and that fashion is going to be dependent on the balanced equation. Since we did not measure out specifically to have exactly the perfect ratios of each of those to produce our products, one of those is going to limit the reaction. So if I gave you 5 bicycle tires and 1 bicycle frame, how many bikes can you make?
One awesome bike.
Only 1 bike. Okay? And you have a bunch of leftover wheels, and maybe you make really awesome bikes. Okay? Those leftover wheels are now in excess. We don't need those. But when we go through to do that calculation, what we're doing is all those simple numbers in our head. We don't have simple numbers anymore. So what we're doing is converting those over into these really massive mole amounts. So now it's 50,423 bicycle tires and 2,462 frames. Okay? Just listed out a bunch of random numbers, And you probably already all forgot what those numbers were, which is exactly what's happening with chemistry. We're not using simple numbers. We're using these big complex numbers. What's the only way that we can make sure that we do a proper conversion across? You write it down. You write down all of those conversion steps and you go through that process. Since we don't know exactly how many moles we had of each, we have to calculate assuming, so for the magnesium hydroxide in that blue, we assumed magnesium hydroxide was the limiting reagent. And we went through and we calculated and said, how much could I possibly make? Then we go through it for HCl and we assume that the HCl is now the limiting reagent. How much could I possibly make? Now what we're doing is converting those two, or comparing those two numbers and say, where do I cap out? We're going to cap out once we make the smallest amount, which is going to be the 58.7. If I added more acid, I could potentially get up to that 82.59, but I'm not there. We haven't added that in. Does that make sense?
So once you find that that number is lower, the 82.59 is totally
That
irrelevant.
82.59 is completely irrelevant. So all that time you spent calculating it, kind of down the drain. Okay? But you needed to calculate it so that you could do that comparison. That's all it was really there for. Okay? So it's a neat question because it goes beginning to end everything we've talked about since exam 2. Okay? We had nomenclature, we had equations, we had balancing equations, balancing formulas, we had conversions, mass to moles, we had conversions, moles to moles, we had moles to grams, we had limiting reagent, we had percent yield. All of it is crammed into this one big massive problem. How many of these questions can you expect to show up on the exam?
One, please.
Zero. Okay? I do not expect you to go through and do this on the exam. We started class a little bit late, roughly at 12:45. It is now 1:15. That was 30 minutes to do one question. That's a bit excessive for an exam. Maybe, just a little bit. Okay. I wouldn't even put it on there as an extra credit because almost guaranteed someone's going to spend all their time doing the extra credit question and not answering the rest of the exam.
Why don't you just make like 2 of those questions?
So the idea is to go through and process all the way through this. Okay, that's the idea of this question. This is the ultimate goal. What you're trying to do is we now run any reaction, we mix them, and we have to process all of these individual steps, organize it to get to a final answer. Okay? Where it becomes tricky with percent yield is this last part that I wanted to again mention here. You shouldn't ever get over 100%. Okay? And this is something that trips students up. You're like, there's no way I should have over 100%. So you go through and you run the calculation, and you got 102% yield. What's your gut response as a student? I messed up, I must have swapped the numbers. So I'm going to swap the numbers and run the calculation again, and I get 97.8. Oh, that must be the answer because it's lower than 100%. And you just got the answer wrong. How do you calculate percent yield? Actual over theoretical. Every single time. If it's over 100%, oh well, it's over 100%. Deal with it. But that's the answer that you got. You cannot change the data to match your understanding or what you want it to be. Exciting, right? Okay, questions?
Yay.
It's a good yay. Stupid? Did I get a stupid out of that too? Okay, so there's our big list again. I would recommend you try and attempt it again just as general practice. Okay, it's a good kind of summary for everything that we've done. So theoretically, you guys should be able to go through and do everything within that on your own. And if you can do all of that, there's your test. Okay, you should be able to ace the test because you know all of those steps. Okay, that doesn't mean if you can't do all that, you don't ace the test. Just to clarify. Where are we now? Little bit of last information we want to address. Empirical formulas. It is the fully reduced whole number ratio of the elements within the compound. Okay, that is what's happening with our empirical formula. You'll notice that for sodium chloride and magnesium chloride, we don't really worry about empirical formulas. Okay, because they're always reported in the format of an empirical formula. For instance, sodium chloride, what's our formula? For sodium chloride, for magnesium chloride, MgCl2. Okay. What numbers do we associate with each of those? How many sodiums are there? It is kind of a tricky question. If we're looking at a sample of salt, how many sodiums are in that sample of salt? A lot. Okay. So why do I not write that a lot? And then I'd have probably 50,000 chlorines. Okay? That's still perfectly valid as a formula. It's a pretty crappy formula because we've got to bring in a whole bunch of extra numbers. So what we do is we reduce this to our empirical formula, our smallest whole number ratio. And with salt compounds or ionic compounds, it's really straightforward because we get positives and negatives, everything makes sense, it coordinates, beautiful. Okay? So one of the things that we end up referring to when we look at our salt compounds is instead of calling these molecular formulas, we call them something else, which I think is stupid because I always call them molecular formulas. Formula units. Same thing as a molecular formula. Okay? All we're saying is it's the smallest whole number ratio for an ionic compound. But what happens when we move up to a compound that is not an ionic compound? Does anybody know what the structure of benzene is? It's okay, I didn't expect you to. Those are all C's, by the way.
It's the carbon ring thing, the hexagonal ring thing.
It is the hexagonal ring thing. I should have thought of that being a problem.
Thing that I was frustrated.
Yep.
The bane of my existence.
That is the structure for benzene. What would its formula be?
C6H6.
Well, you can just count them out. It's not that difficult. So C6H6. Okay, 6 carbons, 6 hydrogens. Okay. Does that match the same type of thing that we've got going with our ionic compounds? For sodium chloride, did I write Na6Cl6? Why not? It's an ionic compound. I'm reducing it to the smallest whole number ratio. So why, when I look at the formula for benzene, I'm writing C6H6 and not, say, CH?
What's the actual structure?
What it has to do with is the structure of your compound. Okay. In Gen Chem, for some reason, we've decided that you guys don't need to understand structure, which is dumb, but that's what we've decided as chemists in general. So what we do is we give you formulas, and you have to interpret the formulas as opposed to the structures. If you move into organic chemistry, we do the complete opposite. We only look at structure because formulas are pretty much meaningless. Okay? So what is the difference then between these two formulas? Well, one is the molecular formula because it is referring to the molecule of benzene. The other one ends up being referred to as the empirical formula. Oof, how do you spell empirical? Okay. So if we're going to go through and do some kind of chemical analysis of a compound like benzene, the information we're going to get out of that is very likely going to lead us to an empirical formula, not a molecular formula. Okay. And that just has to do with how we analyze compounds, how we go through and evaluate those. Okay. So, our empirical and our molecular formulas. To get the empirical formula, what we are trying to do, if we think back to benzene, is we are looking at the relationship between C6H6 and C1H1. What did the numbers mean? After the 6's and the 1's, what did those mean?
How many of each?
How many what? How many atoms of each? Does it say anything about the mass? No. Okay. What's our other unit? If we don't like atoms, because atoms are super tiny, can we scale that up to a unit that we could measure? Moles. That also means there are 6 moles of carbon in one benzene structure, or in a mole of benzene structures. For every 6 moles of carbon, there are 6 moles of hydrogen. All that information is stashed in that formula. When we go through and try and solve for these things, or determine our empirical formulas, what we end up finding out is we measure out not a mole amount or an atom amount, but what do we measure? You go into the lab, how do you measure out something? What are you going to measure? Grams. So when we're trying to convert or come up with our empirical formula, we are coming from grams. So as our very first step, what are we going to need to do? Make sure that all the units of the elements within our formula are in moles. So you will convert every atom across into moles. So you will probably be going grams to moles. Okay? The next part is coming up with this percent composition. Okay? Figuring out how much of each thing is in there. Okay? You could potentially do, or you could see that as an alternative. Instead of giving grams, they give you a percent composition. Well, percent meant percent. So per is out of, and cent was 100. So what we can do is say, assume it's a 100-gram sample. If in a 100-gram sample, 60% of it is carbon, what is the mass of carbon in that sample? 60 grams. Okay? Directly translates across. Once we know it's 60 grams, what can we do? Convert it into our moles using our molar mass. Okay? Once we now have everything converted into moles, we now need to make sure that we can get this to our smallest whole number ratio. Because what we've calculated is not the moles within a single molecule, but the moles of carbon in a massive sample. So you're going to get a lot of moles potentially coming out of that. What we want is the mole ratio. So we'll find the smallest mole value, divide everything through by that, and make sure we've got whole numbers. If we have that, there we go. There's our empirical formula. So nice, simple steps. Everybody understands that you can do it all on your own, right?
Sure.
Yeah, I didn't think so. Okay, we'll work through that. How do we get to the molecular formula? There's 2 ways to approach this, which we'll look at in examples because I have to do math and I can't do math in my head. Okay. A couple ways. The mathematical explanation is what's up here. Determine the molecular mass for your empirical formula and compare that to the molecular mass of your actual compound. How do you figure out the actual molar mass of the compound?
Check it. Similarly to elements.
How do we get the actual mass for a percent yield? How do we get the actual mass for a percent yield calculation in lecture? I can go back. How did you get the actual yield in lecture? It was given to you. How do you get the molecular mass for your compound when you're trying to determine your molecular formula? It's given to you. Okay? You can then compare those 2 values. Okay? If the values are exactly the same, your empirical formula is the same as your molecular formula. If they're different, they're going to differ by a whole number. All you got to do is figure out what that whole number is and multiply through your empirical formula. Okay? So, an unknown compound of radium oxide is found to contain 0.726 moles of radium and 12.3 grams of oxygen atoms. What is the empirical formula? Okay? So, first off, empirical formula, it might help if we actually started coming up with a formula for this. What is our symbol for radium? Ra. What is our symbol for oxygen or oxide? O. Okay. How do we know how much radium we need to the oxygen? Well, that is going to come out of the calculation. Okay, so there's no evaluating charges or anything like that. Our calculation is going to give that to us. What number shows up next to the radium and next to the oxygen? What is the meaning of X and Y? X is the moles of radium in radium oxide. Y is the moles of oxygen in radium oxide. Okay, do we know either of those numbers? What number do we know? We know the moles of radium are actually 0.726. It's a really weird looking formula. Why is that a weird looking formula? It's not a whole number. Okay, it's because we haven't solved for it yet. What we're trying to do is start to bring some of this information in. Do we know the moles of Y? We could figure out. Okay, how do we figure that out? Do the math, okay. Moles of oxygen. Do we know how much oxygen shows up in radium oxide? I think I heard someone say yeah. What's that? There are 12.3 grams of oxygen in radium oxide. Can I convert, grams of oxygen into moles of oxygen? How do I do that? Where'd you get that information? The periodic table gives you the conversion between grams and moles. Why'd you not say 32?
Because we're doing O and O2.
It's just the moles of oxygen atoms in this case. We aren't looking at oxygen as an element or in its elemental state. It's not the diatomic gas. It's how does oxygen bind to radium. So it is a single oxygen atom until we can find out different. We go through and do that calculation. What do we end up with? Oh, I was close. So we can now take that information back to our formula, and now what we've got is our formula being radium 0.726, oxygen 0.76875. Those are pretty ugly looking numbers. What do we go through and do? We need to find the whole number value. So what we're going to do is compare those two numbers. Which one is smaller? The radium one. So what are we going to do?
Use it to divide.
0.726 divided by 0.726 will equal 1. 0.76875 divided by 0.72, or I forgot my numbers, 6 equals
Almost
1 point something. Somebody can give me that number. Let's just say it's 19186. How do we then convert this into our molecular formula? Well, it'll be radium 1 and oxygen 1. Do we need to show the ones? Nope. Our empirical formula, right there. There it is. So what we do is walk through the steps that have been provided to us. All we're doing is taking information of what the formula holds. The formula holds the number of atoms, which can be converted to the number of moles. So what we need to do from the information given to us is figure out how many moles of each of those things showed up in our compound and convert that into our equation. Okay? So it's effectively deriving our formulas. Questions on that process? Yes?
So it doesn't matter if it's not really 1?
So you'll notice it's not perfectly 1, but it is darn close. Okay. And probably all of the calculations you run, I see it, give me a sec, you will be almost exactly at a whole number. There are a couple cases where it could potentially not come out as a whole number. It will come out as a half number. So either 0.5, 1.5, 2.5. What does that mean? What do you round to? It's 0.5. It's exactly in the middle.
Let's go with
Double everything. If you double 0.5, it becomes 1.5. It's okay. But if you're doubling that one, what do you have to do to the other? You have to double the other one as well. Okay, so if you end up at a point where your ratio is fractional, like half fractional, double everything through it, and that'll get you there. That happens maybe 1 out of 10 times, and that 1 out of 10 times will probably be in 151. I don't think that shows up in this class. Does that answer your question? Pierre?
So if you get that 1.5, you would just double it?
Double it. So if you had 1.5, you would double it to
Like you were saying, 3.
3. Exactly right. Okay, so let's just pull this out as a random kind of effect here. Let's just trust that my math somehow works backwards. Let's say you do this calculation and that's what you end up with, 1 to 1.5. What's your formula? If we wrote radium and then oxygen 1.5, that doesn't work, right? We can't have half of an oxygen atom. So what we'll do is multiply the whole thing by 2, and this becomes radium 2, oxygen 3.
So why wouldn't it be radium 1.5 also? You just put the 0.5 to the 1.5 on the oxygen, one after 1.5 on the radium.
I did it just for the sake of this question. I just said let's make that 1.5.
Would that be balanced?
If you're really gonna push me on this, 1.4. That's still not right. I can't do that math in my head. Don't make me do that math. We're just saying it's 1.5. Okay, so here, let's do it this way. Ha, deal with that. Okay, so if our radium came out at 1 and our oxygen came out at 1.5, right? Our empirical formula would come out as Ra2, or radium 2, oxygen 3. Does that make a little more sense to you now, Pierre? And then, what do you mean by balanced? Interesting question. He's asking about balancing of charges. Do we need to worry about balancing of charges in this case? No. The experiment said this is what we got, period. This is what you follow. Okay. Empirical formula. This one's going to be a little... Yes, because I have a feeling there's another part to this. Yep, there it is. Good. So, we'll have you go through and do this calculation. An unknown sample, and this is typically done with compounds that are non-polar covalent bonds, or polar covalent bonds, not ionic bonds. Why? Ionic bonds have charges that we already know. We can predict the formulas based off the charges. Why can we not predict formulas for our non-polar and polar covalent bonds? We're not looking at a charge, we're looking at an oxidation state. We can't determine that. That has to be calculated. Okay? So when we're looking at, say, carbon and hydrogen, we have to go through this empirical formula, molecular formula issue. Okay? So what I want you to go through and do with this question, we found out that a sample is composed of 24 grams of carbon and 2 grams of hydrogen. The process of doing this is elemental analysis, just so you know. What is the compound's empirical formula? For those grammar Nazis out there, I apologize. What is the compound's empirical formula? If you've got questions, raise your hand, I'll come to you. In theory, when you go through and do this calculation, you should have come up with the formula CH. Okay. I noticed a bunch of people went through and said C2H2. Okay. Your calculation is correct, but you aren't solving for the empirical formula. So you got C2H2 because you said there's 24 grams of carbon. We convert it into moles of carbon using the molecular weight. So 12 grams, 1 mole, and we get 2. And then we had 2 grams of hydrogen. We're converting that across grams hydrogen, our molecular weight for hydrogen, 1. Those of you that decided to use more sig figs, good for you. You're still going to get the same answer. Okay. This gets us to our mole values. Remember, there's one more step. We don't just slide the mole values in, even though these are whole numbers. What we have to do is now divide by the smallest number. Well, the smallest number in this case is 2. So we'll divide both of these by 2, and we end up with 1. Our smallest whole number ratio is 1 for each. So our empirical formula becomes CH. That is your answer. Will you see C2H2 as an answer? Absolutely. Okay? Because that is the natural response out of this as part of the calculation. It is not the empirical formula. The empirical formula is the smallest whole number ratio. The reason why we can't immediately assume 2, okay, if you're saying it's 2 for each, what you're saying is you took 1 mole of the substance and degraded it into the carbon and the hydrogen. We said nothing about how much of that original substance we degraded down. Okay? Without that frame of reference, we don't know how many moles we started with. We don't know if this ratio is exactly right or not. So we have to take it to the smallest whole number ratio. Here.
Not to knock out a step, but if you have the same exact number, can you just slash it out?
Well,
You know, you understand what I'm saying? Because you're gonna be, it's kind of, I don't want to say common sense, but you're gonna be taking out the,
so what I would argue is that you aren't cutting out a step by not writing divided by 2 divided by 2. What you are doing is doing that step in your head. Okay? You are still doing that step. You've just internalized it. We've gone through this a bunch of times throughout the semester too. Internalizing things can lead to mistakes. So if you write it down, particularly if you now come back and check your work, if you just ended with 2 and 2, you might go, oh, I must have written the wrong answer because my work says 2 and 2. I should have C2H2. If you've written out that step, you now have something I can say, okay, that's why I wrote CH. Does that make sense? So a lot of what I'm telling you to do on writing stuff out and always showing that work is kind of a test-taking strategy. Because you should, in theory, go back and check your work. Right? And if your work is complete, you can check your complete work. If it's not complete, you may have internalized a step when you first did it. If you go back and check your work later, you've now done the entire exam, your brain is shot to crap, and you're now trying to guess at what you were thinking about 45 minutes ago, which could have been right and could have been wrong, and your thought process is now going to be off. So that's why I want you to write out the work. Would I take off points if you had stopped? So let's say this was a short answer, and what you had given me was this as your work. And you said this was your final answer. Would I take off points for that? Absolutely not. Because I fully understand that you can do 2 divided by 2. Okay? I do understand that. But I'm not the one bubbling in your answer choices. Okay, does that kind of make sense? Other questions on that? Okay, the next step. Take that information that you just solved and now determine what the actual molecular formula is for the compound. So what do we say to do? You take your molecular formula, mass, and you divide that by your empirical formula, mass. The molecular formula mass was given to you to be, thanks for jumping in there, 78 grams per mole, divided by your empirical formula mass, 13 grams per mole. How do we figure out that empirical formula mass? You know the empirical formula, just figure out its molar mass. So it'll be 13. So we get 78 divided by 13, and we get 6. Okay. So that means to get my molecular formula, I need, and I'm going to try and write this out, need 6 CH units. How could I write that out into a molecular formula? One option is CH parentheses 6. We would not write the 6 out front because the 6 now specifies an amount in a reaction, not in a formula. Okay, so our formula numbers would be at the bottom. So we could write it as CH parentheses 6. That looks a little bit weird, particularly because we could translate that 6 inwards. And we'd end up with the formula C6H6. There's our molecular formula. Okay, which is, for those of you really paying attention, benzene, which was the example we just talked about. Okay. Okay. Full circle, yay. Okay. Yeah. Oh yeah, it's even circular. The other way to approach this, okay, instead of going through and doing these calculations, right, you can kind of just piecemeal it together. Instead of looking at the mathematics, just how do we add these in? You know your empirical formula is CH. That means every carbon has to have 1 hydrogen. So you cannot break that unit up. That has to stay. Right? That gives you a mass of 13. So if the empirical formula and the molecular formula were identical, what would the mass be for your molecular formula? 13. Has to be the same if they're identical. It's not 13. So what do we do? Well, let's say instead of it being 1 carbon, 1 hydrogen, it's 2 carbons, 2 hydrogens. Now what happens with the mass? It goes up, but it doesn't quite get there. So you can keep adding carbons and hydrogens in, maintaining that ratio. Okay? You have to maintain that ratio. It's the whole point of the empirical formula, is to give you that ratio on building.
So just guess and check.
Okay? And it is guess and check. For something like this, where you have to do it 6 times, that's a bit tedious. Okay? But what you might expect on any kind of exam, hint, hint, is it's not that big of a number. Okay? It's probably a little bit less work to translate that through. Ultimately, you're still just comparing those numbers and how many times does that 13 fit in there. And what that gives you is then our very last, second to last slide. There's our summary again for how we calculate our empirical versus our molecular. Okay? Questions? Okay. Wednesday is the exam. Thursday is the exam. It is written, it is done. Did I post an announcement about the rough breakdown on it? Okay. That does hold true. I just forget if I've done it or not. So if you've got questions, please don't hesitate to ask. Send me email. Post answers to discussion board. Do something like that. You should be reviewing at this point, not working on the practice exam.